तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the second lecture in Module 2 on losses in prestress. In today's lecture, we shall cover two types of losses in prestress. The first, friction, and the second, anchorage slip. And then we shall learn about the force variation diagram due to both these losses. The first one is the friction. The friction generated at the interface of concrete and steel during the stretching of a curved tendon leads to a drop in the prestress along the member from the stretching end. Now, unlike the elastic shortening, where the loss occurs throughout the length of the member, the loss in prestress is more towards the anchored end and less towards the stretching end. That means the loss progressively increases from the stretching end towards the anchored end. The loss due to friction does not occur in pre-tensioned members because there is no concrete during the stretching of the tendons. That means the friction and anchorage slip both are typical phenomenon for post-tension members. Now, the main reason of the friction is the curvature of the tendon, and from the curvature there is a vertical component of the prestressing force. This figure shows a typical profile of a curved tendon in a continuous beam. On one side, we have the jack and the stressing equipment, and then over the first span, the curve profile is as shown towards the left. Near the support, the curve goes upwards, and then again the tendons come downwards, and finally it gets fixed at the anchored end. That means in a post-tension beam, the curvature of the tendon is the root cause of the friction in the tendon. Now, in addition to friction, the stretching has to overcome the wobble of the tendon. The wobble means that the tendon is not perfectly straight when it is stretched, but it is slightly twisted, and to overcome that twisting there is some additional force is needed. Now, the loss due to friction and wobble are usually grouped together and they are termed as the loss due to friction. The formulation of the loss due to friction is similar to the problem of belt friction in machines. The sketch below shows the forces acting on the tendon of infinitesimal length dx, where this tendon is curved in a circle. R is the radius of the curvature, d alpha is the angle subtended by the length dx, P is the force towards the stretching end, and there is a friction in the opposite direction. The force in the other side is P plus dP, Later on we shall see that dP will come out to be negative, and hence which will imply a drop in the pre-stress on the right side, and we see that the friction generates due to the vertical component of the pre-stressing force, whose resultant is denoted as N. Now P plus dP and N can be put together in the form of a force triangle which is under equilibrium, and from there we can derive an expression of P. Just to summarize, that in the previous sketch, P is the pre-stressing force at a distance x from the stretching end, R is the radius of curvature, d alpha is the subtended angle. Now the derivation of the expression of P is based on a circular profile. Although a cable in a post-tension beam has a parabolic profile based on the moment diagram, the error induced is insignificant. Now how do we quantify this friction? The friction is proportional to the coefficient of friction between the distressing steel and the concrete, or say the duct, and the second one is the resultant vertical reaction from the concrete on the tendon, which is equal and opposite to the vertical component of the pre-stressing force, and this vertical component generates due to the curvature. Now from the equilibrium of the forces in the triangle, we can write that the vertical component N is equal to 2p times sine of the angle d alpha by 2. From a Taylor series expansion, an approximate relationship is 2p d alpha by 2. Hence, the vertical reaction is equal to p times d alpha. That means the vertical reaction is proportional to the pre-stressing force, and also it is proportional to the angle subtended, which is a measure of the curvature. The more curved a profile, the higher will be d alpha. The friction over the length dx is equal to mu times N, equal to mu times p times d alpha. Thus, the friction depends on the following variables. First, the coefficient of friction, second, the curvature of the tendon, and third, the amount of pre-stressing force. The other phenomenon, the wobble, this is affected by the following variables. First, the rigidity of the sheathing, second, diameter of the sheathing, third, spacing of the sheath supports for a continuous beam. Usually the sheets are supported by some supports to have the curved profile. The spacing of the sheets is also influential in determining the wobble. The type of tendon and the type of construction, whether it is a segmental construction or not, the wobble depends on that. The friction effect due to wobble is assumed to be proportional to the following. First, the length of the tendon. That means the longer tendon we have, the longer will be the effect of the wobble. And second, the amount of pre-stressing force. That means the more pre-stressing force we want to apply, the more resistance will be there due to the wobble effect. For a tendon of length dx, the friction due to wobble is expressed as k times p times dx, where k is the proportionality constant, which is termed as the wobble coefficient or coefficient of Webb effect. Now, based on the equilibrium of forces in the tendon for the horizontal direction of the sketch that we have shown earlier, the following equation can be written. On the left side, we have P acting towards the left, On the right side, we have P plus dP acting towards the right, and then we have this total frictional force which is also acting towards the right. The total frictional force is the summation of the friction due to the curvature and the wobble effect, which is also proportional to the length. From there, we get this differential equation, dP is equal to minus mu p d alpha. Again, it is a minus k p dx. If the terms are within bracket, then the sign changes to plus. Thus, the total drop in pre-stress, which is dP over length dx, is equal to minus p d alpha minus k p dx. This differential equation can be solved to express P in terms of x. The solution procedure is similar to a conventional differential equation. That means we are dividing both sides by P and we are integrating the expressions on the left and right from a distance 0 to a distance x. At x equal to 0, the pre-stressing force is denoted as P0. At x, the pre-stressing force is denoted as Px. The subtended angle at x equal to 0 is 0, and the angle subtended at x is equal to alpha. Now, once we integrate, then we have the logarithm of P varying from P0 to Px is equal to minus mu alpha plus kx, or finally we have Px is equal to P0 times e to the power minus mu alpha plus kx. Here P0 is the pre-stress at the stretching end after the loss due to elastic shortening, if any. Like, say, as I said, that there can be elastic shortening in post-tension members due to sequential stretching of the tendons. Now, here we have got an expression which gives the variation of the pre-stressing force over the length. What we realize is that due to the friction and the wobble, the pre-stressing force is not constant over the length of the post-tension member. It drops in an exponential form. Now, if we have small values of mu alpha and kx, which is usually the case because both alpha expressed in radians is a small value, k, the wobble coefficient, is also a small value, then the exponential term can be simplified by the Taylor series expansion, and we have a simplified expression which is Px equal to P0 times within bracket 1 minus mu alpha minus kx. And here we can see that the variation of P with x is a linear variation which drops from P0 as x increases. Thus, for a tendon with single curvature, the variation of pre-stressing force is linear with the distance from the stretching end. If we plot the variation of the pre-stressing force, then we see that this is a post-tensioned beam with a curved tendon where the jack is at the left end. The pre-stressing force is P0 at the left end, and then we have a dropping pre-stressing force which is denoted as Px for any value of x which is measured from the stretching end. Now, in order to get the value of Px, we need to know the friction coefficient mu and the wobble coefficient k. In the absence of test data, IS 1343-1980 provide some guidelines for the values of mu and k. For steel moving on smooth concrete, mu is equal to 0.55. For steel moving on steel fixed to the duct, mu is equal to 0.30. For steel moving on lead, mu is equal to 0.25. And we see that the coefficient of friction drops if the interface of the steel with the duct becomes smoother. The value of K varies from 0.0015 to 0.0050 per meter length of the tendon, depending on the type of tendon. Usually, these values will be provided by the suppliers of the tendon and the duct. Now, let us work out a problem to find out the loss due to the friction for a post-tension beam. Here we see a beam whose cross section is 100 by 300, spanning over 10 meters, and it is stressed by successive tensioning and anchoring of 3 cables A, B and C as shown in the figure. Each cable has a cross section area of 200 millimeter square and has initial stress of 1200 megapascal. If the cables are tensioned from one end, estimate the percentage loss in each cable due to friction at the anchor end. For the problem, mu is equal to 0.35 and K is equal to 0.0015 per meter. And the sketch shows that cable A has a negative eccentricity at the end, that means the CGS is located above CGC, and at the center it is having a positive eccentricity of 50, whereas cable B does not have any eccentricity at the end but has a positive eccentricity at the center. Cable C does not have any curvature throughout. The eccentricity is constant, which is positive 50 throughout the length of the beam. What we can realize is cable A is more curved as compared to cable B, which is again more curved as compared to cable C. The pre-stress in each tendon at stretching end is equal to 1200 times 200 millimeter square is equal to 240 kilonewton. Now, this value does not include any loss due to elastic shortening. Now, if we have to compute the pre-stressing loss due to the friction, we need to know the value of alpha, which is the change in the slope of the curved profile of the tendons. To know the value of alpha, the equation for a parabolic profile is required, and the equation can be given by this formula: y, which is the displacement of the CGS from its end, equal to 4 times ym, which is the displacement at the middle, divided by L square, which is the length of the span, times x times within bracket L minus x. This is a second order equation, and which gives the equation of the parabola. And the subtended angle is same as the change in the slope between the two ends of the parabola, which is represented here as alpha over the length L. Now, here ym is the displacement of the CGS at the center of the beam from the ends, L is the length of the beam, x is equal to distance from the stretching end, and y is the displacement of the CGS at distance x from the ends. An expression of alpha x can be derived from the change in slope of the profile. The slope of the profile is given by the first differential, which is dy by dx is equal to 4ym by L square within bracket L minus 2x. At x equal to 0, the slope dy by dx is equal to 4ym by L. The slope at any other point can be computed, and the difference between the slope will give the value of the subtended angle alpha. Now we can note that since the expression of the slope is linear, that means it is a first order function of x, the change in slope will be also linear with x. The expression of alpha x, which is the subtended angle as a function of x, can be written in terms of x as alpha x equal to theta x. That means alpha x is proportional to x, where the proportionality constant theta is equal to 8ym by L square. The variation is shown in the sketch. That means for a parabolic profile, as we are moving from the stretching end towards the anchoring end, the subtended angle or the change in slope is linear with respect to the distance from the stretching end. The total subtended angle for the profile over the length L is given as 8ym by L. The prestressing force Px at a distance x is given by this expression Px is equal to P naught times e to the power minus mu alpha plus kx, which is simplified as equal to P naught times e to the power minus eta x, where mu alpha plus kx has been substituted by a function eta x. Both alpha in the first term and kx, both of them are proportional to x, the distance from the stretching end. Hence, we can substitute mu alpha plus kx as a term eta x, which is also proportional to x. Next, we need to know what is the value of ym. That means the displacement of the CGS at the middle from the two ends. For cable A, the total displacement is 50 at the left plus 50 at the middle, which gives total 100 millimeters or 0.1 meter. For cable B, ym, the displacement is equal to 0.05 meters, and for cable C there is no displacement, it is a straight cable, and hence ym is equal to 0. For all the cables, the length is equal to 10 meters. Now, if we substitute the values of ym and L, then we get the expression of eta x for each cable. Eta x is equal to 0.0043x for cable A, 0.0029x for cable B, and 0.0015x for cable C. And eta x is a measure of the drop in the prestressing force, and what we can observe that it is highest for cable A, which is the most curved profile out of the three, and lower in cable B as compared to cable A, and it is the least in cable C, because the only drop in the prestressing force is due to the effect of wobble in cable C. The maximum loss for all the cables is at x equal to L equal to 10, the anchored end, and for that e to the power minus eta L is equal to 0.958 for cable A, 0.971 for cable B, and 0.985 for cable C. The percentage loss due to friction at the anchored end is given as 1 minus e to the power minus eta L times 100. That means what we are doing is that we are calculating the prestressing force at the anchored end, subtracting that from the value at the stretching end, and we are dividing that by the force at the stretching end. Like that, we are getting the percentage loss, and we are multiplying that by 100. Now, once we do this, the results are 4.2% for cable A, 2.9% for cable B, and 1.5% for cable C. That means the percentage loss in cable A is maximum, the percentage loss in cable B is in between cables A and C, and the percentage loss in cable C is the minimum. If we plot the variation of the pre-stressing force, then we find that from the stretching end, the pre-stressing force drops the least for cable C. The green line is for the cable C. The drop in the cable B, which is a brown line, is in between cable A and cable C. And for cable A, the drop is maximum, which is given by the red line. That means this conforms to the concept that the pre-stressing force will drop more for cables with higher curvature. The loss due to friction can be considerable for long tendons in continuous beams with changes in curvature. The drop in the pre-stress is higher around the intermediate supports where the curvature is high. Let me explain this by a sketch. What we see in a continuous beam, the curvature changes. For the first span, it is the profile is bowing down. Then over the support, the curvature is in the reverse direction. There is a point of contraflexure between these two. And again, when we go to the second span, the curvature is in the same direction as in the other span. That means for a continuous beam, the cable changes curvature, and this leads to higher drop in the pre-stressing force. There is one angle subtended by the first curve, there is another angle which is subtended by the second curve, and there is a third angle which is subtended by the third curve. And what we see that this angle will be the highest out of all these three. Now the pre-stressing force, as we said, the drop is proportional to the length x, and it is also proportional to the curvature. Now since the curvature in the span is lower than that at the support, the pre-stressing drop is relatively low, but over the span the pre-stressing drop is high, and then again when we go into the span region, the pre-stressing drop is low. To summarize, if we are stretching the cable from one end, the pre-stressing drop is uniform for the first curvature. it will be steeper over the supports and again uniform for the other span. The longer the beam becomes, the more curvature the beam has, there will be larger drop in the prestressing force. To remedy, to reduce the loss, is to apply the stretching force from both ends of the member in stages. That means to reduce the drop in the prestress due to friction, one way is to first stretch from one side, next bring the jacks to the other side, stretch the other side, repeat this process and get a more or less uniform prestressing force. If more than one jack is available, then the stretching can be done from both the sides. Next, we shall learn the concept of anchorage slip. In post-tension members, when the prestress is transferred to the concrete, the wedges slip through a little distance before they get properly seated in the conical space. The anchorage block moves before it settles on the concrete. There is a loss of prestress due to the consequent reduction in the length of the tendon. This sketch will animate the process of the loss due to anchorage slip. What you can notice is that as the prestressing tendon is released from the jack, the wedges sit in the conical space, the anchorage block gets slightly depressed within the concrete, and this sum total effect is called the anchorage slip, which has a reduction in the length of the prestressing tendon and which leads to a drop in the prestressing force. Thus, the anchorage slip is another phenomenon which leads to the drop in the prestressing force. Now, the total anchorage slip depends on the type of the anchorage system. Usually, the suppliers of the anchorage block will provide some data to calculate the anchorage slip for their particular system. In absence of manufacturer's data, some typical values of some systems can be used. Now, the anchorage slip is given by the total slip, the distance by which the prestressing tendons shortens because of the setting of the anchorage block. It depends on the system, like for a Fresinet system with 12 number 5 millimeter diameter strands, the slippage is by 4 millimeters. For 12 number 8 millimeter diameter strands, the slippage is by 6 millimeters. For Magnal system, it can be 8 millimeters. For Dwidac system, it can be as low as 1 millimeter. Now, due to the setting of the anchorage block, as the tendon shortens, there is a reverse friction. Now, this is an interesting phenomenon that when we are first stretching the tendon, there is a friction in the opposite direction of the stretching force. That means, if we stretch towards the left, the friction acts towards the right. Now, when we are releasing the jack and the anchorage block is sitting on the post-tension member, the tendon is trying to move from left towards the right. For a certain distance near the stretching end, the friction reverses, and this phenomenon is called reverse friction. That means, it does not allow the movement to occur throughout the full length, but the shortening happens only in a limited region of the tendon. Hence, the effect of anchorage slip is present only up to a certain length of the member. Beyond this setting length, the effect is absent. this length is denoted as L set. For friction, what we have seen that the drop in the prestressing force is occurring throughout the length of the member, but for the anchorage slip, the reverse friction restricts the drop within a certain length of the prestressing member, which is close to the anchoring the stretching end, and that particular length is called the setting length, which is denoted as L set. If we plot the force variation after anchorage slip, what we observe is that before the tendons were released, the prestressing force was dropping linearly. But after the tendons have been released and the anchorage block has set, there is a drop in the prestressing force at the end, but this drop is not reflected throughout the full length because of the reverse friction. This drop reduces as we go away from the stretching end, and after a certain distance this drop is not present. Now, both the friction and the anchorage slip causes a variation of the prestressing force along the length. We can plot the variation of the prestressing force in a diagram which is called the force variation diagram. For a post-tension member, the magnitude of the prestressing force varies along the length of the member due to friction losses and setting of the anchorage block. The diagram representing the variation of prestressing force is called the force variation diagram. This diagram is helpful if we are interested of the loss of the prestressing force throughout the length. It gives an idea that at what location we have the higher drops in the prestressing force, and how can we improve the variation with stretching the cable from the two ends either sequentially or simultaneously. The force variation diagram helps us to determine the anchoring process for a continuous beam, because in a continuous beam the force variation is quite significant, and unless we take a rational measure to do the stretching process, we will not be having an idea how much to stretch at each of the ends. To draw the force variation diagram, we are again reverting back to the expression of Px. Considering the effect of friction, the magnitude of the prestressing force at a distance x from the stretching end is given by this expression. Px is equal to P0 e to the power minus eta x, where eta x has both the effect of friction as well as the wobble. Eta x is equal to mu alpha plus kx, which denotes the total effect of friction and wobble. The plot of Px itself gives the force variation diagram. Now, the initial part of the force variation diagram up to length L set is influenced by the setting of the anchorage block. Let the drop in the prestressing force at the stretching end be denoted as delta P. The determination of delta P and L set are necessary to plot the force variation diagram, including the effect of the setting of the anchorage block. That means we have an expression of Px which is satisfactory to plot the force variation diagram for most of the length of the beam, except near the stretching end, where over a certain distance there is a drop in the prestressing force from Px due to the anchorage slip. Considering the drop in the prestressing force and the effect of reverse friction, the magnitude of the prestressing force at a distance x from the stretching end is given as follows. this equation is analogous to the equation that we have seen for friction. The difference is that the new value of the prestressing force, which is given as Px prime, this is in terms of the reduced value of the prestressing force at the stretching end, which is given by P0 minus delta P times e to the power minus eta prime x. Now, here eta prime is for reverse friction, that means the friction is occurring in the opposite direction and is analogous to eta for friction and wobble. Now, remember that for a reverse friction, Px prime increases with the distance from the stretching end. If we plot the two equations, the first equation gives a dropping curve from the value of P naught with x, the distance from the stretching end. The second equation gives an increasing curve which corresponds to the reverse friction, and at a certain distance both these equations give the same value and the two curves intersect. Now, the distance from the stretching end to this point is the setting length, and which is denoted as L set. Again, in this curve, the dashed line is the original force variation diagram after the stretching. The orange line is the variation of the prestressing force after the anchorage slip, and the blue line is the variation of the prestressing force beyond the setting length, which is due to the friction effect. Now, our next task in hand is to derive an expression of the setting length. In order to do that, we are substituting x equal to L set in both the expressions of the forces. On the left, we have the expression of Px. On the right, we have the expression of Px prime. And this equality is satisfied at x equal to L set. We are transposing the terms related with the exponential, and here we are again using the Taylor series expansion, and we get this the third form of the equation, and then we are writing an expression of delta P, which is the drop in the prestressing force at the stretching end, which is proportional to the initial prestressing force times the sum total of the two frictions, eta and eta prime, times the L set. And we can express the reverse friction in terms of the friction in the tendon. Since it is difficult to measure the reverse friction separately from the friction that we have seen earlier, the reverse friction is usually taken equal to the frictional values that we use in our conventional calculation of the prestressing loss. If we take eta prime equal to eta, then the expression of delta P simplifies to the following. That means the drop in the prestressing force at the stretching end is equal to 2 times the prestressing force times the friction eta times L set. Now, the following equation relates L set to the anchorage slip. See, we can calculate delta P from the slip that is provided by the manufacturer of the anchorage block. The slip is given as half times delta P divided by AP EP times L set. This is the expression of the slip which relates it to the setting length. Now, once we substitute the expression of L set from this previous expression, we can find an expression of the slip in terms of the L set, in terms of the initial prestressing force, the friction term eta, and also we have the reverse friction. Transposing the terms, we have brought L set on the left and the delta S term which is available from the manufacturer on the right, and we are also simplifying eta prime equal to eta. From this we get an expression of L set. The L set is equal to the square root of the slip times the area of the prestressing tendon times the modulus of the prestressing steel divided by the initial prestressing force and divided by the friction term eta. Now, what we can understand is that the setting length is proportional to the square root of the slippage. That means, the more slip we have for a particular type of anchorage block, we shall have a longer L set, but the variation is a square root variation. The term P naught eta, it represents the loss of prestress per unit length due to friction. This we can derive from the expression of Px, that P naught eta is the loss of prestress per unit length. Now, once we have determined L set and we know the drop in the prestressing force from the value of the anchorage slip, we can draw the force variation diagram including the effect of anchored slip. Now, the force variation diagram, as I said before, is used when stretching is done from both the ends. It is a rational tool to determine how much force we need to apply at each end and what is the sequence we should follow, and finally what prestressing force variation are we expecting in the member. That can be available only if we draw the force variation diagram. The tendons are overstressed to counter the drop due to anchored slip. The stretching from both the ends can be done simultaneously if we have more than one jacks, or it can be done in stages if we just have one jack. The final force variation is more uniform than the first stretching. The following sketch explains the change in the force variation diagram due to stretching from both the ends in stages. For this post-tension beam, the stretching is done from the right, and we can see that there is a variation of the prestressing force as we move from right towards the left. Now, once the tendons are released on the right side, there is an anchorage slip which leads to a drop in the prestressing force near the stretching end, but the drop is reduced till the drop becomes 0 at the distance L set from the stretching end. The second sketch is the variation of the prestressing force after the anchorage slip at right end. Next, we are moving the jack to the left and we are restretching the tendon up to a value which is equal to the value on the other side originally. Now, when we are applying the tension on the left side, there is a drop in the prestressing force, just like as it happened when we stretched from the right end, and this curve, the green curve, meets the previous curve near the center of the beam. Now, once we release the jack at the left end, there is a drop in the prestressing due to the anchorage slip, and that drop again reduces, and finally it becomes 0 at a distance L set from the distance from the left end, which is now the stretching end. Thus, what we observe that for this single span beam, if we are stretching it from both the ends sequentially, the force variation diagram is more uniform compared to what we had got after the first stretching from the right end. To summarize, the initial tension at the right end is high to compensate for the anchorage slip. It corresponds to about 80% of the characteristic strength, and the force variation diagram, in short FVD, is linear. After the anchorage slip, the FVD drops near the right end till the length L set. Then the initial tension at the left also corresponds to about 80% of the characteristic strength. The force variation diagram is linear up to the center line of the beam. Now, after the anchorage slip occurs, the force variation diagram drops near the left end till the distance L set. It is observed that after 2 stages, the variation of the prestressing force over the length of the beam is less than after the first stage. If we do a few more stages, we shall observe that the variation will be still lower and the prestressing force will be more uniform than the variation which we had obtained after the first stretching. This is more relevant in a long continuous beam where the drop in the prestressing force is even higher, and there a sequential prestressing or a simultaneous prestressing from both the ends is the method to reduce the effect of the drop in the prestressing force due to friction over the length of the member. If we are stretching from both the ends, then the force variation is more or less symmetric about the center line of the beam, and that is desirable when the beam is loaded symmetrically. To conclude, today we talked about 2 more immediate losses of prestressing force. The first loss was the friction, and due to the friction, the force drops from the stretching end as we move out from the stretching end. This can be severe for longer beams and for continuous beams, because what we have found that the drop in the prestressing force depends on, first, the amount of the prestressing force, second, the length of the prestressing beam, and third, the curvature of the prestressing tendon. Now, for a long continuous beam, there is reversal of curvature of the prestressing tendon, and the drop in the prestress is even significant near the intermediate supports, because there the curvature is high, and hence there can be a significant difference between the prestressing force at the stretching end and the prestressing force at the anchor end. In order to rectify this, we need to know the variation of the prestressing force over the length, and then we can use the force variation diagram to stretch it from both the ends. The other type of immediate loss that we have observed is the anchorage slip. This occurs due to the setting of the wedges in the conical space and also the setting of the anchorage block in the concrete. The anchorage slip is usually given by the manufacturer of the anchorage system, and the effect of the anchorage slip is of course limited within a certain length called the setting length from the stretching end. Now, the force variation diagram can be drawn to understand the variation of the prestressing force along the length. We have solved a differential equation to express the prestressing force in terms of x, the distance from the stretching end, and we see that the drop is almost linear with distance. If we incorporate the drop due to the anchorage slip, then we have an increasing curve at near the stretching end up to a distance L set from the stretching end, and after that it drops down. The force variation diagram can be rationally used to have a more uniform prestressing force throughout the length. If we are loading the prestressing beam symmetrically, then it is always preferred to have a symmetric force in the prestressing member, and if we are loading it sequentially, what we can see that we can achieve a force variation diagram which has less variation than compared to the diagram which is obtained after a single stretching. With this, we are finishing the immediate losses of the prestress. In our last lecture, we had covered elastic shortening. Today, we covered friction and anchorage slip. Now, all these three losses occur during the prestressing process, and it is felt immediately during the stretching, and hence all three are grouped under the immediate prestressing loss. Next time, we shall start the other group of loss of prestressing force, which is the long-term prestressing force, which depends on time, and these are affected by the creep and shrinkage of concrete, which is the variation of the length of the concrete member with time, and it is also affected by the relaxation of the steel, which is the drop in the prestressing force under a constant strain, and this long-term losses becomes a function of time which we need to monitor to get the final effective prestress. Thank you.